Hey, welcome back. Okay, we've all been looking at using optimal policies and how we want to do them. So how do you find them? So let's talk about how we can actually compute an optimal policy. Alright, so we're going to suppose the random variables are x1 to xn, and the utility only depends on some subset of both the random variables and the decision variables. So the utility depends on that. So now let's look at the expected utility given some particular policy. So given a policy. So what we're going to do is we're going to use this as the product of all the worlds given the policy times the utility of this whatever subset of the variables it is. Okay, so it's all of these given the policy and times utility. So now this is the world given the policy. Well, we can just write that down as the probability of xi given the parents of xy times this utility, except now we have to choose the best decision at each point. So this is the expected utility. And what we'd like to do is we'd like to choose pi that maximizes this. So that's what we're going to do. We're going to choose pi to maximize this. And those are just a sum of products. And so if we maximize each part of a sum of products, we get the maximum. Okay, so when we give it a sum of products, if you have a choice between something big and something small, we're going to choose something big. Okay, that's what we're going to maximize. So what we're going to do is sum out all the random variables to compute the expected utility. So all we're really doing is computing the expected utility, except at every opportunity, we're going to choose the policy to maximize the sum. So when decision variables in a factor with only its parents, we're going to select the maximum value at all times. That way we're going to maximize this expected utility, and we're going to choose the pi that maximizes the expected utility. So effectively the algorithm is just going to compute expected utilities, except at the right opportunities, just when it can, it's going to select the pi that maximizes this. And because it's just a sum and product, as soon as if we have a choice between two factors, we can choose the maximum one. Alright, so here's in more detail. We're going to construct a factor for each conditional probability and a factor for the utility, as we did before. We're going to repeat. Now we're going to sum out random variables, but we're going to sum out those that are not parents of a decision node. So we're going to sum out all of those that are not parents of a decision node. And then we're going to let D be the last decision node. So there's going to be a last decision node, because assuming for now that we have a no forgetting one, there's always a last decision node. Now if we've summed out all of the variables that are not parents of a decision node, these only in a factor with some of its parents. So that's what we have there. So these parents here are things that are going to be observed. So what we can do is we can eliminate D by maximizing. So once we have D, we can choose the maximum value, but because it's in with some of the parents, we can choose it associated with each set of parents. We can choose the maximum. This creates two things. One is an optimal decision function from D, which is just the argmax of D of F. So instead of doing sum, we're just doing max, but argmax finds the argument that's the max. A new factor we're going to, instead of doing the sum over D, we're going to max over D in the factor. Okay, and we're going to do that until there are no more decision nodes. And now, just like we did when we're computing any variable elimination for queries, we're going to sum out the remaining variables because there still might be variables left. And we're going to multiply the factors, and this is the expected utility of an optimal policy. So let's look at the umbrella decision. So there are three factors in here, and it's probably most useful if we look at the app here. So here is the app. There's a weather forecast, a weather umbrella. So the umbrella depends on the forecast. The satisfaction depends on the weather and the umbrella, and the weather forecast depends on the weather. So what we're going to do is to sum out the variables that are not parents of the decision node. So it's only weather. So let's go into this. So we're going to click on Optimize Decisions, and we're going to go now into verbose. Okay. So the factors now are there are three factors, one of which is this factor, which is the utility. So this is the utility we saw before. Okay. Then there's another factor for the weather. So it's going to be sunshine with 0.7 and rain with 0.3. And then there is the factor which is the conditional probability of forecast given the weather. So if the weather is sunshine, here's the distribution of the forecast. And these three sum to 1 and these three sum to 1. Okay, they're the three factors. So what we're going to do is to sum out weather. And this is exactly the same we did before. We're going to end up with a factor on forecast and umbrella. So it's the factor of forecast and umbrella. Okay, so if we now look at one of these things here, then we'll see that we can't see very well, can we? That the probability of forecast is we're going to look at these two factors where we're going to look at one where it's sunshine, the weather is sunshine, and we're going to do the same one where the weather is rain and do this. So this is how we're going to compute this. Okay, so you can look at it as a better size. Okay, we could do each of these. So this is just summing out. We've seen this before. So now what we can do is now we get to choose an umbrella. So now for each value of the forecast, it's sunny, we want to pick the maximum one. So let's look at the two values for umbrella. So when the forecast is sunny, which is the top two values, we'll look at these two values here, and we can choose the maximum one of these because we eventually want to get the maximum utility. So we know that we can just choose the maximum because it's adding and multiplying. There's no subtraction or dividing or anything else that's involved. So you can always just choose the maximum. So we're going to choose this 49. So we're going to leave it at home if it's sunny. If it's cloudy, we look at these two values. We choose the maximum, which is leave it at home if it's cloudy, and we get 14. And if it's rainy, we're going to leave it at home. So we can choose the maximum. We're going to take it with also 14. Okay, so that's what we're going to do by maximizing. So we're not going to add, we're just going to check to the maximum of each value. Okay, let's eliminate that. Okay, now we have this forecast. So we had 49, 14, and 14. So that were the maximum values. We also have a decision variable, which is the forecast, which was the maximum value. So it was sunny, it was leave it at home, cloudy, it was take it, and it was rainy, take it. Okay, let's look at this factor again. So this factor here was forecast, but now we've got to marginalize out this. We've just got to sum over these three. So we're just summing out these three values. So all we're doing is this big sum over products. We've just got to sum over. That's going to give us the expected utility, which is 77. So it was the sum of those three values. And the decision function is, if it's sunny or cloudy, leave it home. If it's rainy, take it. So that's what we're going to. That's our policy. Okay, let's look at another example here. Let's load the fire alarm decision problem. Okay, this is okay. And now, remember there's two decision variables and utility depends on those three. So now we're going to, maybe I'll view this font size, medium, make it smaller. We're going to optimize decisions in verbose mode, and that's going to give us this. Okay. And now here are all the factors we had before. It's the factors of the conditional probability table. We have a variable, one for each variable and one for the utility. One for each random variable and one for the utility. Right, and this one here is the utility one. Whoops. Smoke, check smoke, speed smoke. Oh, this is the probability of cease smoke given we check smoke. This is my utility node that we had before. Okay, so what we're going to do is we're going to eliminate all these random variables that are not parents. So we're not going to eliminate cease smoke. We're not going to eliminate check smoke or report or call. We're going to sum out all these variables. Let's sum them out in some arbitrary ordering. Doesn't matter what order we choose. And we end up now with a factor on call. So now factor on call, cease smoke, check smoke, and report. So this on its parents. Whoops. So let's look at what happened here. So what we had here was we had this factor on call, check smoke, cease smoke, and now we're going to choose, and now we've got this factor. So we just summed it out just like we did before. Now, whenever it's report, check smoke, and cease smoke are all true, we get to choose whether we call. So we're always going to choose the maximum one. We can choose minus 1.33. Okay, Okay, when it's report is true, check smoke is true, and see smoke is false, we're going to choose the maximum one, which is minus 3.68. When report is true, you don't check smoke, but you see smoke, then we get to choose any one. Now these are 0. It turns out that this has 0 basically because it's impossible, but we don't really care. It's easier just to maximize anyway than to start reasoning about whether it's possible or impossible. So we're going to keep choosing the maximum one. Okay, so the maximum variance these, we're going to check two things here. Well, the decision function is going to specify with report, check smoke, and you see smoke, we're going to call, which is what we decide was the maximum value. If it reports was true, check smoke is true, and you see smoke is false, you're not going to call. And this one was true, which is because they're both 0. Okay, and we also have a factor now, which is the value between report, check smoke, and see smoke. We get this value. When a report is true, check smoke is true, and see smoke is false, you get this value. All right. And the reason we could do this is because we're actually allowed, because we can, this appearance of it, we're actually able to just change our mind about call for every assignment of values to these. So now what we've got to do is now we've got to marginalize out see smoke. And now we end with a factor on check report and check smoke. And the report and check smoke here, when report is true, we get to choose whether we check smoke or not. So we're going to choose the maximum one, which is minus 5.01. When report is false, we get to choose the maximum one here, which is minus 17. Okay, so that's what we're going to do here. We're going to eliminate this. We're going to choose the maximum one of each time. One of those is the decision functions can be the function between report and check smoke, and the other one's the value. The other one we're going to construct as new factor, which is just the value of report. So let's eliminate check smoke. So the decision function is if it's report, we check the smoke. If there's no report, we don't. And the current factor is just those maximum values. And now we've got to sum out report, and we end up with the utilities minus 22.5835. Okay, so that's all we're going to do. All right. So we did that. All right, so here's an example we'll think about in class. So here's a one here that says that what we're going to do is we have someone has a disease, and the disease produces the symptoms, and from the symptoms you decide what test to take. So when you have a test, you don't observe the disease, instead you observe the symptoms. And then the test result depends on both the disease and the test. It's basically, the symptoms are essentially independent of it. And then from the treatment, we only get to observe the symptoms, the test and the test result, and that gives the outcome that depends on the disease. And we'll assume here the utility depends on the cost of the test and the outcome. So how good or bad the test is plus the outcome. So the first question is, what are the factors? Then we're going to ask which factors get summed out first. Okay, so think about that. Think about which decision variable is eliminated after those ones. And then what factor is created. Then what is eliminated and how is it eliminated? And what factors are created after maximization. Right, so let's look at the complexity of doing this. So let's suppose the decision D has K binary parents and B possible actions. And how many assignments of values to the parents are there? Well, there's K parents, so there's 2 to the K assignments of values, because there's one for each assignment of a different value. So the number of decision functions is then the number of, for each of these you get to choose B, so it's B to the 2 to the K. Okay, so it's B to the 2 to the K, and that's usually a lot. However, when we're optimizing this, what do we do? Well, we're optimizing each of these separately. For each of these 2 to the K assignments, we're choosing one of the B actions separately. So instead of doing that, looking at the number of decision functions, all we are doing is we're doing 2 to the K optimizations. And each of them chooses B different values, so it's B times 2 to the K. So that's for one decision variable. So it's, okay. Now let's look at all of the decision variables. If you want to do the number of policies, there's the product of all of them. The product of B, BI to the 2 to the KI, of all of those values. And optimizing this But optimizing this only takes the sum of all of these values. So this turns out to be exponentially better than searching through the policy space. Okay, so this is exponentially better. So there's one algorithm we have now that's exponentially better than searching through policy space, which is something we might do. Okay, let's stop there and we'll talk about more in a minute. Thank you.